The Hunter-Nash method is used to determine how many stages are needed in a liquid extraction. And in this screencast, I just want to concentrate on explaining how to obtain the mixing and operating points in the ternary phase diagram. And other screencasts go through determining the number of stages and do example problems. I'm going to look at just two stages to make it easier to understand what's happening. And keep in mind, each of these stages, the outlets are assumed to be in equilibrium. And so the situation we're looking at is we have a feed, and I'm going to use the notation F to indicate the number of kilograms or kilograms per hour. And what this consists of is a solute. This is what we're trying to remove from the feed extract. I'm going to call that A. And a carrier that the solute is dissolved in. And entering countercurrent flow is a solvent, S indicating number of kilograms. And the idea is that the solute is going to be soluble in the solvent and we can extract it. So what we're going to see then, leaving these stages, and for now we're going to not worry about the flows between. There clearly is flows, but let's not worry about them now. Let's just look at the final extract. And so this is, we'll call this E1, and the notation is, because it's leaving stage 1, we'll call it E1. And this is essentially the solvent that has been enriched in our solute. And then leaving stage 2 is the raffinate. We'll call it R2, and 2 because it's leaving stage 2. And so this is a depleted feed. So our feed loses some solute and exits stage 2. So what we're doing to determine the mixing and operating points is to do mass balances. So first I'm going to do an overall mass balance. And so that just says that the flow into my system, let's make it clear, flow in is going to equal the flow out. And I'm using the colors to make it clear where these terms come from. So the flow in is F plus S. And the flow out is E1 plus R2. Okay, so straight total mass balance. This flow kilograms per hour. Important thing to keep in mind, looking at these extraction system, this is at steady state. Steady state and equilibrium in each stage. So each stage, the phases are in equilibrium leaving. So the total flow is what we're going to use. We're going to indicate this now as M, and that's what we're going to identify now on our ternary phase diagram. So you can look at M as being the composition. It's going to have a composition that results if we just mix together our solvent and our feed and measured its overall composition. And of course that has to be the same as the overall composition of the two streams leaving, because we're at steady state. So now let's look at the ternary phase diagram. So I've taken a simplified view. I don't have the tie lines or any of the grid on this, but the solute, that's A. The solvent, we're going to assume this is pure solvent. It certainly have some of the solute in it, but in general, we'll look at just pure solvent. And then we have the feed at some composition. Well, I'm just going to assume the feed is 45% solute, and we want to separate it from the carrier. And so if I draw a straight line connecting them, then any point in between would have a composition corresponding to mixing different amounts of feed and solvent. In other words, if I mix them 50-50, then a point midway in between solvent, and we'll call this S, and that's what's in our mass balance, the number of kilograms per hour. It has a composition of pure solvent. Any point in between is just the average of how much of each of these. So again, a 50-50 mixture would be halfway in between. So I'm going to draw a line connecting these. Now let's suppose And we have options in terms of how this is done, but in terms of doing the calculations, suppose we know F, 100 kilograms or 100 kilograms per hour, and we know S. In general, of course, we're going to have to determine these depending on what output we like. Well then, if I was to do a balance on the solvent, I could determine the overall composition, the final composition of the solvent. So what we want to identify is if we mix these two together, what would be its composition? Where is that on our ternary diagram? So just a simple mass balance, mixing these together in the solvent. So I have so much solvent, so it's pure and initial. The final, we have a mass fraction of the solvent in this mixture M, and the total flow is the two added together. So this is 150. We're going to solve for this mass fraction, and this is 100 plus 150. So that means that this is 0.6. Well, that defines a point on our phase diagram. So let's locate the point where the mole fraction solvent is 0.6 on that line. And the way I would do that is to just draw a line, and that's solvent fraction of 0.6. So this then, let me remove those lines so it won't get too crowded on the diagram. So this is the mixing point M. So I'm going to specify concentrations. It's going to be on this phase envelope here because remember, we're going to get phase separation in this region. So here's the extract concentration. So this is E1. Right? This is the solvent leaving enriched in the solute. Because of our earlier mass balance, if we were to draw a straight line between these points, it's going to intersect the phase envelope here, and this is our raffinate R2. The idea here is that if we're to mix E1 and R2, we should get an overall composition of M because that's what our mass balance says. If we mix E1 and R2, we're going to end up with that mixing point, and it has to have the same composition as if we were to mix S and F, those two streams, because this is a steady state process. So the lever rule then tells us how much extract and how much raffinate flows we have, because if you notice, lever rule, it would say that this distance here times E1 must equal this distance here times R2, where R2 is the number of kilograms per hour. And if I just make the measurements for that, I find that R2 is equal to 2/10 of E1. And that's strictly from measuring these two distances with a ruler. Okay, so that's just applying the lever rule. What we want to do now is another mass balance to get the operating point. So we found the mixing point, and that then defines, once we have sufficient information, in this case specifying the extract concentration, defines for mass balances the raffinate leaving the entire system. So I have identified this operating point, and this is what I use in determining number of stages. I need the tie lines in this diagram. I've left them out just so it's less complicated, and for brevity we're not going to do the next steps, do that in a different screencast, but the idea here is that hopefully now you understand how we get the mixing point and the operating point just from mass balances, overall mass balances, and mass balances on the stages for liquid extraction.